Right. So the next speaker is a Cristóbal Moya, who is talking about the Lyman Alpha double peak at redshift 7.
Can you see my screen?
Yes.
Yeah.
Great. So I will begin then. Okay. So good morning, good evening. My name is Cristóbal. I'm a PhD student at the Pontificia Universidad Católica de Chile. I'm currently on my second year of my PhD. And today I want to talk about an interesting profile that we have found in one of our lager sources. So the first thing that I want to talk about is Lyman Alpha profiles. So Lyman Alpha profiles observed in the local universe in Greenpeace galaxies, such as the one that I'm showing you here. This is a figure from Young and collaborators 2016. You can see that you recurrently often find these double peaks in your Lyman Alpha lines. The reason that you find this is due to radiative transfer processes. So as the photons try to escape from the region where they were emit, they either get absorbed, scattered, redshifted, blue shifted, and so on. So that's why you don't see a single peak, but you see this blue and red wing with a gap in the middle. I have included an arrow here for you to indicating this gap. And why is this gap important? Well, so the results from Greenpeace galaxies indicate that there is a correlation between the escape fraction of photons and the separation between the peaks. If you have a larger separation, you might think that you have more radiative transfer effects, thus photons have a harder time escaping the galaxy. If you have no separation at all, you might think that the photons are escaping without much trouble, so you have a higher escape fraction. And also, I would like to remind you that these Greenpeace galaxies are believed to be analogs, low redshift analogs of the sources that are found in narrowband service such as Liger. And you can imagine why the escape fraction is an important quantity for reionization studies. What about double peaks at higher redshift? Up to date, 3 Lyman Alpha emitters have been reported at the redshift larger than 6. So you have Cola 1, Nebula 4, and A370. At these high redshifts, as you go into the epoch of reionization, you would expect that the neutral IgM would absorb the blue wing of this profile. So if you see a double peak, you can think of two scenarios that are happening. You can imagine two things from your source. One is that there is an ongoing escape of radiation, because you can measure the separation between the peaks, and you can then imagine that the escape fraction is non-zero. And you can also imagine that your source sits within a ionized region of the universe. And due to the Hubble flow, the radiation, the Lyman alpha line gets redshifted out of the rest frame wavelength, and thus is no longer affected so heavily by the neutral IgM. Next, I want to talk just a bit about the Lager survey. So Lager survey is a narrowband survey that uses the special filter NB964. That is the one indicated in this plot by that orange arrow. The filter is installed in the DECAM instrument. So DECAM is really nice because it has a very good red sensitivity, as well as a large field of view of 3 square degrees. The filter is built such that the center matches Lyman alpha at a redshift of around 6.9. And we aim to obtain 30 hours per field, and are currently aiming to get 8 fields in total, meaning 24 square degrees. So once that we find our narrowband selected candidates, it's time to confirm them. Of course, you want to confirm these objects to see if you are actually you're actually able to find these Lyman Alpha emitters at this redshift. So far, our spectroscoping campaign using the IMAX and LDSS3 spectrographs at Magellan Telescope have confirmed around 50 Lyman Alpha emitters within the larger survey. So even though the spectra was taken to confirm the nature, we see that not all Lyman Alpha emitters are equal. We see that there is some profile, there is some structure in their profile. But in order to study this properly, we need a higher spectral resolution. So the spectral resolution of this data is around 200 kilometers per second. So enter CDFS1. This is the object of interest. So in 2019, Yang and collaborators presented Magellan Fire spectroscopy for the brightest source in our Chandra Deep South field. Lyman Alpha is detected at a redshift of 6.925. The goal of this study was to find nebular lines and to see the structure of the Lyman Alpha profile. No nebular lines were found. There seemed to be two peaks in the Lyman Alpha line, but the resolution they achieved was not so good as to make that claim of a double peak. We recently got new observations of this object with Magellan Fire. We got around 7 hours of exposure time with really good conditions, and we use a smaller slit than the one used in Yang et al. 2019. So the spectral resolution was around 50 kilometers per second. And our goal was still to find, to search for double peaks and see if we could secure any nebular lines. So let's go into the results. So of those 7 hours, we stacked 5 hours that were the one with the best conditions and the high signal to noise. The Lyman Alpha line is clearly detected at both the 1D and 2D spectra. And also, a double peak appears in both of them. You can see how the spectra has these two peaks, indicating a double peak, of course. But this wasn't enough. We wanted to see if we could say anything about the geometry within the slit of the system. So what we did next is that we stacked only the data that had the same position angle of the instrument. So this is important. I must mention that the fire spectrograph maintains a constant parallactic angle during your observations, meaning that the object will not have the same orientation in your slit throughout your observing run. So we stacked only the data that had a similar rotation angle. That left us with 2.5 hours of exposure time. Then we did 3 different extractions. We had this ABC. A is the lower one, like the bottom one. Then we have B, the top one, and C, which include both extractions. So what we find here is that the double peak might not be due to radiative transfer effects and might be related to a velocity gradient. The reasoning behind this is that you can see that A has most of its flux redwards, whereas B has most of its flux bluewards, and the combination of both of them gives you this double peak. The separation of the double peak is around 100 kilometers per second, meaning a high escape fraction. Actually, from empirical relations taken at lower redshift, this would indicate a 100% escape fraction, but these relations had not been fully calibrated at high redshift. And the blue wing extends up to 120 kilometers per second from the line center. So as a conclusion of future work, we report the discovery of this Lyman Alpha profile with a double peak at a redshift of 6.9. The small separation between the peaks suggests a high escape fraction, and the extension of the blue wing gives us a minimum ionized bubble, a minimum size for the ionized bubble of 0.14 megaparsec per megaparsecs. We are currently in the process of securing more more sources with layers. With this, we are in the process and we have obtained more spectroscopy data for us to further study this. In particular, see if there's any correlation with these profiles and the environment of the sources. Thank you very much. I will be more than happy to answer any questions.
Right. Thank you, Cristóbal. So time for questions.
So what are the Lyman Alpha luminosities here? Or what is the Lyman Alpha luminosity here? Comparable with low Z galaxies showing double peaks? And also another question is the continuum detected? Do you have an equivalent with?
Right. So I'll answer the second question then. So no continuum is detected on this source. And the Lyman Alpha luminosities, this is bright. This is like a 43.3. Like the logarithm of the Lyman Alpha luminosity is around 43.3. So this is the brightest source in our CDF field. But I do not know what are the typical luminosities of lower redshift galaxies that present double peaks. But I can tell you that this is on the bright end of our sample.
Right. So then next question is from the other Rohan Naidu. So how common is the profile you find among the green peas, low Z analogs? Does the imaging show any hints of merger?
Any hint of what, sorry?
Merger. Galaxy
right,
merger.
Okay. So as far as I understand, these profiles are really common in your local green peas. Yeah, you often find this. I couldn't put a number to it. For as you go up to higher redshift, they become rarer and rarer because you need an ionized region for the photons to escape, and you need high resolution spectroscopy in order to resolve these double peaks. So they are not so common at higher redshift. As I mentioned, at this high redshift, there's only 3 of them found. But yeah, I mean, at low redshift, they are pretty common, but at higher redshift, not so much. But I'm unable to put a number to that.
How likely is it that something spurious appears given the noise, etc.? If you just forward model the noise, how many times could an apparent double peak appear?
Mm-hmm. So in order to prove that, at some point what I did was just stack random exposures. So take a subset of the exposures. It consistently appeared. So the double peak was consistently found in both the 1D and 2D spectra. So we discard that, or we don't think it might be due to something spurious. Also, in the young 2019 paper, there were already some hints that this might be a special profile, and this has a rather high signal to noise. So we don't expect this to be a spurious detection. I'm sorry, I just realized that I didn't fully answer the previous question about the merger. The narrowband image just looks like a single source. There's no hints for it to be a merger.
Right, thank you, dear Cristóbal. So I think many other questions are on the Slack, but it's time. So let's move on. So thanks, Cristóbal again.